Well, I got some ideas on what changes to make on your stack transformer circuit. So I was beginning to wonder if I cannot draw an analogies between this and this. Oh, this is the wrong one. This is off. Where's the on one? There it is. Maybe I should get rid of the off one. Confusing me. Okay. So here we have the DC loop. And this is the reduced full diode bridge, reduced down to 2 diodes, and it still works. And here's the AC loop. Here's the load ground branch. And this is the DC supply branch, or the stimulus. It's not really a supply, it's more like a stimulus. And this is a little ballast that helps for it to go in there, and an extra high fuse to make it possible to reduce this down to 2 diodes, 3 times the remaining fuses, which are 1,000 kilo ohm, or 1,000 ohms each. This is 3,000 ohms. So I was beginning to think, since this is a DC loop here, what if that's the DC loop here when you have the battery here, and then this transistor in here is the diodes that are here, because these diodes are acting as switches. Now that would mean that if this is the AC loop, then that would mean that everything to the right of these stack transformers, maybe I should shrink this. Everything to the right here is the AC loop. And that means this high voltage, now in deference to what Bob French's schematic conveyed, this was the low voltage down here. So I turned the whole schematic around by 90 degrees clockwise in order to fit it in the screen. So he had this as the low voltage and this is the high, but because of creating this, well, I don't know if it's because of the regulator or because I took, microcap requires a ground. There's no way to avoid it. Well, all simulators are like that. So I took it, I assumed to put it on the negative of the battery, but I took it off and moved it over to what had been the high voltage output, and now it becomes the low voltage output, which makes sense because the ground is there. And it also worked correctly in order to replace the resistor, the 1,000 ohm resistor that Bob had as his regulator, with this diode neon bulb setup. And I was able then to take out the 1,000 ohm resistor that was located here as well. See, so it's not required to have resistors anywhere in the circuit. I only have them here because they serve as solder joints. Now, before I put in all the solder joint resistors, and when I had this regulator figured out, and the ground over here, but I only had battery here. I did not have the impulse waveform generator here. It looked promising, but it was momentary. The simulator at first showed me a humongous gain of voltage up in the, I deleted it because it only happened that once, so since it was non-repeatable, I couldn't count on it. But it was e to the 15, I think, 10 to the 15th power was the gain, was the voltage, because I'm only measuring voltage across these 2 points, because I'm assuming they're on no load. This is a no-load test, so if this is the load. Now, if I can draw if this is indeed nothing more than a voltage multiplier, then, using inductors, stack transformers instead of capacitors, and the fact that you're stacking them makes them look like a ladder, then it may be, since this is nothing more than a voltage multiplier, it may be possible to piggyback or tack on certain elements of this onto that. And since this is the DC loop here in which I connect the stimulus source, yeah, it's hard, it's impossible to call it a voltage source. It's more like a stimulus source onto the DC loop. That means that I need to take out this voltage source here, keep this as a closed loop, put an inductive ballast here in its place, and then come off here with a branch to this assortment of 10 grounding rods with adjustment caps attached to them. So, sorry for the suckers, to clear my nose. So I'll start by copying that. And I will put it down below. Ooh, tiny. Might fit in there, maybe. I might as well put it to the left. Can always move it. Okay, take that out. And let's see, put in this. Now the statements have to be put in. So let's see. Yeah, this has to go. I don't know. Let's see. Put it. Oh, this is too high up. Oh dear. I see what I have to do. I have to turn this on its side. I have to make sure the polarity is correct. So, this is for labeling purposes. And when I look at the oscilloscope tracing, I'll know which side is, if it gives me positive results, I'll know what it's telling me. Might as well put a connecting wire. Okay. Let's see. Oh, I forgot what I was doing. Guess I'll put it here. Okay. Then we need this to define the earth. What else? Oh yeah, the inductive ballast. Oh no, wait, I also need, I don't need the fuses, do I? No. But I need the adjustment cap. Oh, right, I can't. Oh, I don't use it there. Okay. Now I need this thing. Now that's positive going to... See, that's the other thing. Which side is positive? I may want to put in fuses on your circuit. They may help. They may help. I don't know. Let's see. Positive was up here. So all I have to do is match that. So let's see. All right. So now I give it a new name. So what's this one? With grounding rods. Neon bulb. With diode, neon bulb, and 10 grounding rods. Might as well make it a number 10. Oh, I know what I have to do. I have to put in the text. So I'm going to move that over. And, whoopsies. Move this to here. Make it nice, neat, and tidy. Okay, that'll be better. Now, let's see, what is this one? Actually, that could be moved. No, I don't have to. All right, now I'm going to go out. There we go. Oh. Huh? No bar there. That's strange. Oh, here it is. I need glasses. There we go. All right. Save that. Now let's see. What are we looking for? There's no load at the moment. So what are we going to test? Oh no. The high. Yeah, right. The high voltage points. The high. Missing model statement. New model. Oh yes. I bet that's. Huh? Really? You don't say. Okay. Go over to here. Adjustment cap. Model. Oh dear, I did all of those separately? That's a lot of work. I guess so. Oh, that's right, yeah. So I got a little work. Well, no, I think I know what I can do. Let's see. Yeah, these don't have any model statements. So let's see if I check out. Yeah, see, this is number 5, and there is no number 5. So what I do is a shortcut. I go to the models. Which one is it? Oh dear, so many different possibilities here. So just the caps. I'll have to pick it out. So we get Notepad. And then what I could do is put it on another notepad. Any more ins? Inductors? Yeah, towards the bottom. Oh, they're all inductors. Whoopsies. Yeah, there you go. Then we take all of these and we go to here, go to model statements. Uh-oh. Whoa, what is all of this? Three-phase power source, general. I don't use that anymore. Oh, from file utility. Sinusoidal source. We're not using a sinusoidal source, so I can take that out. And now I'd be stuck with stuff I don't even possess anymore. So let's see, there are no caps. No, there is. There's a model 2, but it's empty. So let's eliminate it. Okay. Whoops, there's another cap. Wait a minute, what's all up here? Oh yeah, it's got the transistors. Oh, it does have a cap of resistance 3, and that's model number 1. Oh boy. Yeah, this one has, okay. It already has a model 1. Oh, those are 10s. Well, let's see if I need it. There's no cap in here anywhere. Right. So I don't think I need that. Okay, so I'll take that out. If I could find it. Where are you? I saw you before. There you are. So now, why do, oh yeah, the inductors, okay. Alright, so there's the caps. See if it gives us any warning messages. Save it. Huh, no warnings. Alright, so we're going to be looking at high, low. The current on this doesn't exist anymore. And then all of the power levels. So, this is 3, 4, 5, 6, 7. Oopsie. Oh shit, they were supposed to be combined. Well, maybe this time they should not be. That's pretty poor. Not very good. Oh, you know why? Because I'm missing one thing. This ground here should not be there. Ooh, but I have to be there. No, not anymore. So I'll take that out. And try again. Maybe a little better. Oh, I gotta change these things. Alright, let's, whoopsie. See, everything is 2, so I don't like, my eyes are so poor. Everything I'm looking at is fuzzy anyway, because I don't like wearing glasses and wearing the microphone headset at the same time. It pinches my skull. There. There, now I got nice lines. But certainly nothing over unity. It looks like there's a surge in the beginning. Yeah, that's what this circuit seems to tend to do. It's just a momentary surge, and then it flattens out. Whoopsie. Try that again. Okay, let's see. Let's try increasing the time frame. Something's increasing. Oh, look at that. Goody gumdrops. Now, you notice here these are triangle waves. That's a good sign. And what is this? PGT. Wait a minute. There is no power source anymore. Yeah. Yeah, I love it when it does that. It gives you a reading even though there's no power source. Do I see a power source anywhere? There's no power source on this thing. It does not exist. It does not exist. It does not compute. New. Well, now it's regulator and ground source. Call that a ground source. Alrighty. So let's try for 1,000 seconds. Uh-oh, it's exploding. Now you got your over unity. So that's all this circuit needed was a whatchamacallit, it had to be seen, interpreted in the proper way. Now what is this telling me? 17.5 seconds. So that's okay. 17.5 seconds. So if I go for 20, 1, simulator doesn't simulate accurately very well if you use whole numbers for anything. So I put in tiny little fractions, you know, so many place values, a dozen place values to the right of the decimal point, and then I'll use an assortment of numbers up here on either side of the decimal point, random a sequence of numbers, because the simulator just doesn't give you accurate results unless you create a unique signature or identity to each parameter. So that's why I needed all those model statements to define the equivalent series resistance of all those multiple capacitances. Where are they? I needed all these, and so they look at all. It's all these zeros to the right of the decimal point, and then a series of random numbers, and then I think this is called the mantissa. I don't know. I forget what it's called. The portion to the left of the decimal point is a whole integer, or a round number, 10. And these are the ground capacitors. Here, 3, that would be the adjustment capacitor. Or the other, well, these ground capacitors, the earth capacitors. The adjustment capacitors and the ground cap are 3 ohms of equivalent series resistance, while the earth caps down here are pre-charged with 1 microvolt, initial condition IC. Let's see where we go here. So the earth caps have a capacitance in the area of terafarads, 10 to the power of 12, because that's what I compute the capacitance of the Earth may be if the shell is 1,000 meters thick. and the radius is over 6 million meters of the radius of the Earth. So using concentric sphere formulas for computing the capacitance of two spheres and the dielectric between them, two concentric spheres, then this is what I come up with. And then I give it an initial charge, IC, of 1 microvolt to represent the charge at the surface of the Earth. And then the adjustment cap, which is like a blocking cap because the circuit cannot see the capacitance of the Earth if I put blocking caps in between the Earth capacitance and the circuit. It'll only see the capacitance of the blocking cap, which I call the adjustment cap. And the adjustment cap is my ideal of 100 femtofarads, 1/10 of a picofarad, which I also is the same value of this ground cap here. So, but this is on the main trunk. So I have two blocking caps, actually, now that I think of it. But here, the circulation and vibration can occur. So in a sense, this is kind of like a closed loop, because this is the other end of the closed loop. So I have a loop condition here of, what is this, 9 modules with two capacitance on each shunt, on each parallel junction of this overall large loop. Anywho, so let's see. So assuming we don't replace the transistor with another diode, because we just need 2 in series here, what is the result? Well, let's see. Make sure I save this first. So this is, how long is this? 31 seconds. Sign, it's starting to vibrate, and we're getting up into the 45 volt range on our high to low. Oh, but they're both the same. Oh, because I took away the ground. Right, because I don't need it there to run the simulation. Let's see, nothing else is that high. Everything else is in the same range, it looks like. Now, PGT and PDT are one and the same range, although the spikes, no, they seem to be the same. So let's see, if I put PDT and PGT together, yeah, PDT and PGT. So here's PDT, here's PGT, that's 3. So I put this together, then we can have less. Now we could put, we can put the other 2 together. Okay. Let's make this red, since that's the low voltage. I don't know what good that does. So now, oh, the same waveform. That makes sense, sort of. And exactly the same amount, so you don't even get a voltage difference without a load. Holy cow. So we do need a ground there. Wow. Let's see, so, but when did it explode? Let's find out. So, what is this telling me? This is telling me it can't go any further. But the trend is one of an explosion, so it looks like this thing is going to give you a humongous amount. Let's see. This power stored, that would be the inductors and capacitors, is here. The energy stored is here. So we're storing more power than energy. Which, I don't know, does that mean the time interval is, oh, very small. Right, because things are exploding now, so it has to shrink the time interval. Let's see. EGT is the energy generated, but it can't be anything because there's no voltage source. So I don't know why it's giving me a EGT, or a PGT for that matter. So right, the EGT is less than the PGT by a factor of like 1,000,000. Yeah, about 1,000,000. So it shows that it's using a microsecond as its interval just before it terminates. Or maybe on average. Yeah, probably on average throughout the entire... Well, no, it wouldn't have run so fast. No, it would have been towards the very end. Yeah, that simulator the amount of time in our time that it took to run that simulation was so short that it must have been a very long time interval further back. In fact, if we look at the number values on the left-hand side, look at this, it's like no difference at all. That means it had to have been a very small... Well, but it's the same condition here. What is that saying? It says that the voltage shift... You know, I'm beginning to wonder if that's... No, if we're making analogies here, then that's not the way you're going to run your load. That's right. So we're going to have to get rid of the high and the low voltage. It's going to be on a branch. So let's go do that. So let's see. So there is no... well, no, let's wait before I take that out. So now I want to put this load here. So... okay. And then we come over to here. Whoopsies. And then we want to get this. I really need another sucker. I want my sucker. All right. Now, how am I going to do this? Let me count the ways. Oh, so now I've got a fuse here that I didn't have before. Ooh, interesting. No, that's no good. Okay, well, no, wait a minute, oh, I need the ground. Well, wait a minute. Wait a minute. Oh yeah, it's the only thing I'm missing is the ground. Whoopsies. Why don't we bend that up a little? There we go. Bend it up a little. Well, yeah, just a little. A wee little winky. And connect that to there. Now, this is the load. Let's see, what was the other thing? Oh, fuse. Now I need the fuses. Where is it? Define fuse. Yeah. Since these outputs are not connected to anything, I won't be needing them anyway. So, save this, run it, but now we need the load. Let's see, where are you, load? Oh, no, let's go to the bottom, maybe. So let's see. Now what do we need? We need 1. Oh, we got rid of 2. Wait, what happened to 3? Oh, shoot. PGT and EGT. No. Oh, shoot. Now I forgot what these are. Well, if in doubt, give it a unique identity. Alright, so we want voltage of the inductive load and then we want its current. Whoopsies. And put that in number 8. Give it blue and red. And away we go. Looks even better. So putting the load on, and holy shit, the power dissipated is 125 giga? Wait a minute, where'd all these values come from? Well, not on the load, that's for sure. So what the? Oh, it's wasting it in the ground. Oh my god. Well, you're sending a lot of energy to the ground, that's for sure. Okay, where are we here? We need number 2. Okay, that will work. Okay. Now, I don't need so much time. Whoopsies. F9, 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 where are you? F9, okay. What am I doing? Oh yeah, the time. So if we reduce this to 3, so the voltage outputs are nothing so I'll just eliminate them. So let's go and eliminate that because that's giving us, we will no longer possess them. They are going bye-bye. Okay. The generation PGT is 600U, which makes no sense whatsoever, and the EGT doesn't make any sense. But now the difference between them is about 4,000 to 1. Let's see. So that means 1/4 of a millisecond, which is 250 microseconds. So it looks like the interval, the time interval at the very end is 1/4 of a millisecond. Now the stored power is up in the giga range of watts. The energy is in the range of 1/5 that. Oh, so the time interval for computing, my God, so it's using different time intervals for each different tracing. Now that's interesting. So for the generation, it's using 1/4 of a microsecond, but for the storage of power and energy in the caps and coils, it's using 1/5 of a second, 200 milliseconds. That's interesting. And then, oh, I didn't do that. For the PDT, oh, this is very confusing. Maybe I should get rid of the PGT and EGT because they're not high values anyway. We don't need to know them. Because there's no source. So what am I doing taking, where is it, PGT, taking a reading of the source when there is no source? Delete item. Well, because, oh, well. If I want to do a comparison to find out what the COP is, but you can see high. We're getting energy for free from the Earth. And we've got, so storage, power storage is in the gigawatt range. Energy storage is in the 200 megajoule range. The power dissipated through diodes and resistors is in the about 3 megawatt range. So we're storing, let's see, this is the power stored. Yeah, now I have to do comparisons between the storage and the dissipation. Let's see, the inductive load is not a whole lot of voltage, but the current is even less. But it's exploding. So the circuit is consuming a lot of power. In fact, we can go look at the nodal voltages. Where are we here? And as we see, we've got megavolts here. Yeah, the load doesn't have a whole lot of anything. Your stack transformers don't have a whole lot of anything. So it's basically this section in here is just under a gigavolt on average. And then we go down to the grounding rods. The top of the grounding rod is gigavolts, 14. So it's slightly elevated by comparison to this, which makes sense because it's connecting directly into it. So all of the energy is at the top of the adjustment caps. That's where all the energy is congregating. And then it diffuses and it's reduced in this area where the transistor is. And the left hand, the input side of the first transformer, the split center tap transformer. There's not a whole lot of there's hardly any voltage difference across the spark gap, so the spark gap has not fired. In fact, let's find out if it's fired. I love to find that out. Oh, here's the current flow. The current flow is leaving through this grounding branch, but it's entering through these. So that seems to be the function of these, is to draw current in, but it's not drawing a whole lot. It looks like milli. Let's zoom in there. Yeah, milliamps. So it's drawing in milliamps. Oh, look, it's dissipating here. 0. Well, of course, because it's not connected to anything. Oh yeah, this we have to get rid of. Whoopsies. We no longer need this. It was fascinating, I mean, I must say. Oh, wait. I got rid of it. It changed. No, that can't be. It changed the, oh dear, maybe I need that. But that means it's serving some function. Right. Mitko Gorgiev on Quora, he found, well, yeah, he found out that when you have an extension of metal, it becomes a, well, according to theory, it becomes a ground. It's what did Bob call it? A field ground, or an atmospheric ground. So now we got to raise this back up to 4 to so it takes a little longer to surge, which actually 41 seconds. Oh, now we got tera, even better than giga. Ha ha. So, well, it's worth the wait. Maybe not 41. What was the other one? 31? Let's see. Let's try 32. No? Let's try 33. $34. Now it goes down. 35, 6, 5. Because the simulator takes shortcuts and because it takes guess estimates trying to predict what the outcome will be, it bases its methodology on those guess estimates that are done before it even does the calculations. It kind of does a pre-calculation overview to try to guess what's going to happen, and then it defines how it shall proceed based on that guess estimate. And that's why it keeps coming out different each time, because its guess estimate keeps changing. Look at this, milli. So before you get to the terminus, when the thing explodes, it can do that. It can collapse, and then what is the real value? But see, if you keep taking it longer, now the values go up again. So it becomes a periodic function. The output rises and falls based on how long do you run the thing for, and it keeps bobbing up and down like a buoy. It can't make up its mind, almost. Now we're getting close to the decimal, logarithmic system. 40. We're just under it at 39. That doesn't do anything, so let's do 40. It may not like it. 40. No, see, it was 41 that really did the... See, it's a peculiar, thing. You don't know what to believe. Let's try 42 and see what happens. Now you get to see what I got to deal with, right? I knew there was a reason for doing it. Well, now it's down to G when I use 42. But see, now that's when it cuts off. So the cutoff point here was 19.089 seconds. All right, so if I go back to 41, that's 19.089. Now it's 20. So see, it went longer before it shut down, and so it gave us more results. So it shows that it's a consistent surge. So at the very least, now I hit text and then escape to get out of numeric modality into the graphic. Pretty good. So let's see the wattage. We should do the wattage is what we should do. All right. So instead of that, I will do wattage. That means I make it black. And times. And then copy that, bring it down here, copy that. And now we're going to go for the ohmage, the VI ratio. Oh yeah, these numbers are all wrong. 1, 2, 3, 4, 5. And the color in this I like to make green when it's a VI diagram. I got wattage under 10 watts. Oh, I wanted to see if the spark gap lit. Right, so the spark gap is called neon bulb. Let's go check it out. See, there's current coming in. For some reason, it's bringing current in from this stick, this little piece of wire sticking out that's not grounded to anything. Where's the other one? I took it away. Huh? What? Oh, I don't know what this is doing. Let's do that again. Oh, even more, 67 tera. Holy crap. Oh my god. Oh, so the fact that this is rising here is telling me yeah, it's a voltage surge. So the voltage now is increasing. The impedance is increasing, giving a higher voltage relative to current, which of course we don't want. It's bad enough as it is. Although, what is it? Where is it doing? What is it doing? Oh, what's the lowest? Well, the lowest is at the beginning. It's negative 73 ohms, which is interesting. That makes it look like it's generating there. Oh, so this is a transient. It generates in the beginning. So there is over unity, or else the load would not be... Yeah, see? The load has negative watts here, and that's why it has negative impedance. And that shows that it's generating in the very beginning, but it's only in the beginning for 1 instant of time at 329.84 milliseconds. So at that mark in time, the circuit is generating possibly a humongous amount of power. Let's see. Doesn't look like it. Well, the PST is positive, so we look for the EST. Here's the EST is negative. There you go. So time went backwards. That's right. Wow. PDT. What happened to the other ones? Where is it? Huh? EST, PST, PDT. Uh-oh. Am I missing one? I am. EDT. Well, that's strange. How could I have missed that? Okie dokie. Let's see, what color should we use? Well, power could be, oh, I don't know. If that's red and that's, well, maybe magenta's okay. Alright, so we got EDT versus PDT. So the PDT, oh, it's both in the giga, but this is 5 times less. No. 5 times more. No, 4 times more. So that's a quarter of a second it's using. But the fact of the matter is, the storage is now normal. Oh, so there's... Right. So at the end, it's functioning in a normal manner. It's only... let's see. It's only... See? Negative, positive. Oh, it's 0? Right. So here, positive, positive. Wait a minute. This is both... No, the watts is negative. Oh, so now it looks like... Oh, wait. We have to go here. That's the problem. Oh, dear, 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 dear. Okay, now... Positive, negative, positive, positive. So the power, so let's see, which one was negative? This one. The storage. So the caps and the coils are generating. Totally. They're totally generating at the very beginning. And then at the end, they're not. Oh dear. That's not nice. Oopsies. Oh, that's not going to work. Ah! Ah, shit. Well, let's start all over again. When in doubt, start over. Yeah, there's not a whole lot of generation going on in here. What else can we do? Oh, now the current is going out. All because I took away that thing. I shouldn't have taken it away. Unbelievable. So what is this? Well, the storage is still pretty good. No, it didn't help. Now, I think it's when the other one was there that it helped. Yeah, let's do that again. One more time. One more for the road. No, it's still going out. Yeah, it didn't help. Although it's coming in here, although that's strange, but it's 0. I don't know. Alright, so it's always best to simplify anyway. It's hard to imagine that this is not over unity since you're getting the energy for free. You're not getting a whole lot before it freezes up. Now apparently the dissipation is less than the storage. Well, not apparently, it is. By a factor of maybe, what, 50 or 500 or something. Let's see, if this is 70 tera and this is 200 giga, then that would be 5 times 70 is 350. So it's storing 350 times more energy than what it's dissipating, which is a good sign. It shows that it's accumulating, which is what a voltage multiplier... Well, I don't know. The load, that may not be the best place to put the load, though. The load is pretty minor. The watts are not good. And the ratio proportion wasn't very good, as I recall. I think it was like 40 to 1. Uh, 20, yeah, 18. So I wonder where we would put the load. Well, let's see. Let's move on. That was current. Power. So PD is power dissipation. PS is power storage. See any high numbers? No. It's all pretty low. Very low. Yeah, everything is low. So it's not storing much power. I wonder why it tells me differently when I do the p-val, when I do the function, the total, the t function. Well, I don't know. Strange. Let's see, what was that? Power? Whoopsies. No, that's current. Condition. So the diodes are off. All the diodes are off. Oh, oh wait, these two diodes are on, and these two are on. They're on, but they're not hot. If they were hot, it would say so, but it's not. I can move that over. So that told us everything. Conditions, power, current. Oh yeah, voltage. The voltage is not too bad on that side. But here it gets into the giga range. And here it gets into the tera range. So get a lot of voltage up in here. And that's probably because, see, the current is coming this way, and it's coming this way. Oh no, it's leaving. Oh, wait, it's coming, yeah, it's separating. So it's going in reverse here by comparison to all of the tops of the grounding rods, it's going down. So, isn't that weird? It's almost as if this top portion here is generating. Oh, let's try taking out the this connection here. And so now the switch is broken. See what happens. Oh my God, it's worse than before. Holy shit. Oh, and now the load is similar in watts to the total power. Oh, oh, Nelly. So you see, things are different in different universes. Oh my God. Oh my God. So now the current is still minor. Oh, but here now we got mega amps. Yeah, now here the current is very low, but to the right here, oh my God. Yeah, these transformers are going through a tremendous amount of current in the mega amp range. Oh my God, this is tremendous. I wonder if the neon bulb came on. See, I keep forgetting to, what did I do differently? I can't remember now. Oh, I took out the 4 of the grounding rods. So let's see, that was the current. And what's the voltage doing? Oh, now it's up in the giga range all the way to the right. So now, for some reason, the thing is actually functioning the way you would expect it to. Because, oh, it looks like this may be on because the voltage difference is quite different. Yeah, the neon bulb, it looks like the neon bulb came on. So you see, if the neon bulb fails to come on, then you don't get the gain. So the neon bulb is intrinsic to this thing. But now how much is going through the neon bulb? Mega amps, the same as what was going on behind it. Let's see, how are the power level? Well, we got tera over on this resistor here. We've got storage. So we've got a tera. Oh no, excuse me, that's 15. That's 1,000. 3,000 tera. Is that watts? Yeah, I think so. Yeah, power, P. So that would be watts. 3,000 terawatts stored on this. No, on the coil. Yeah, on the coil. E to the 23? 40? Yeah, what is that? Dissipation. So the Earth is receiving this a tremendous amount of power going into the Earth. Yet, this grounding cap, look what it's dissipating. Well, but it doesn't, yeah, it's dissipating like almost nothing. And these resistors, almost nothing. And these adjustment caps, almost nothing. Wait a minute. No, this is on the left-hand side. Oh! Oh, wait a minute. I'm looking at the right-hand side. That doesn't count because it's not connected to the circuit. What? Oh, no. What if... Oh, that is bizarre. Oh, I just got this weird idea. If I eliminate these, whatchamacallits, and rerun, will I get the same answer? Oh, this could be weird. $19, I get even more. It was 15 before. Wait, we better run this a second time, just to make sure. It's stable. You don't have to, oh my God. So you get even better results when they're pulled out of the ground. So we had too many. So actually, oh my God, 21? E to the power of 21 for what's being dissipated? Shit. But if you have to keep them in the ground to serve as your brake, apparently that's a braking mechanism. But that's, so I don't know how to turn this thing off yet. Probably we need a switch right in here. How much you want to bet? But first let's find out how much power we can get from this. So let's take out another ground. Oh my God, this is too much. Let's try taking another one off, because you never know. Oh, it's like nothing. It's comatose. So that's the magic. Oh, so there you go. So if you break it at that point, okay. So we go backwards. So the magic was here, right? But this was the greatest power gain here. So that means if I take this out and I take the broken switch and put it here, it should be nothing. But we have to run it longer just to make sure. So let's go E to the, I don't know, 8, 7, 6, I don't know, 5. Let's do, what is that, 6, 5? I can't see. Uh-oh. Oh, you get a spike. Oh, so it's not enough. Should probably take out more. Let's see. Let's take this and move it over to here. Whoopsies. Oh, I have a different spacing there. That's not fair. Aw. I want everybody to be equal. Just because it makes it easier to work with this. Come on now, go over there. Alright. So we move you over to here. Yeah, it's too long a period of time. Huh. Oh, and this is growing down into the negative range? Do you know what that means? It's, ooh. Hey, that means you're getting more amps than volts. Wow. And it's generating too. How do you like that? What are the numbers? Negative, positive. So it's generating now. Well, no, it's the storage. The storage is generating. The dissipation, though, is normal thermodynamic. And, oh, yes, both the watts and the VI is negative. So you're getting some generation in the caps and coils. Right. That makes sense. But it's still not... I don't understand. Oh, this one's not spaced properly either. There we go. So I gotta save that. It's still spiking. This is no good. So it's 1 million seconds. Let's see, 1 million. This is 40. A million, maybe 5 would do it. No. Oh, what is it doing? Yeah, it's trying to generate, but it's all in the low value. So I guess you don't have to worry. Maybe not. Or I don't have to worry. See, reduce this to 4. It's humming there. Look at that. It's vibrating. Oh, and then it's spiked. It's a single spike. It doesn't continue the spike. So it only happens once. And all the values are low. Oh, so let's... Yeah, negative 24, femto, negative 22, pico, negative 39. So that looks like it's off. Let's go put this back here. So it's still off. So it's got that surge in the beginning, and then it just flattens out. Well, actually, it's got 2 surges here. It's got one over here at this point, and then one over here at this point. Some kind of surge. This would be voltage. So the voltage surged here, even though the power surged earlier on. So it looks like reversed logic of how to turn this thing off. Very strange, but... Oh dear, let's see. Whoopsies. Hey, come on. If I hit the right keys, hotkeys. Okay, so this is turned off too. It's behaving the same way as before. Well, that's good to know. At least it can be turned off. But it's like night and day, the difference between the two. So it's comatose. It's not really off, but as good as being off. And then we put this back here. But let's take this one off. So now the switch is here. Oh, it's still off. You never know what you're going to get. Sometimes I can run circuits that I haven't run for a year and I get completely different results. So it kind of makes you want, because they're unstable over unity circuits by definition, are unpredictable. Yes, a wild stallion. It's better than saying a wild teenager. A wild stallion. They want to run free. Alright, so now we put this back in. Well, no, I'm going to have to read. Okay, so now we should get the gain. No, we don't. Uh-oh. Not good. Uh-oh. Oh. Nope, not good. So I had to take it for a longer period of time to get past that freeze. See, that happens. You run it longer and you get different results. So I gotta bring back each grounding rod. That doesn't look right. Oh no, that's right. Just because I diminished the number of rods and then I went and increased them, so it changed its perspective. It's almost as if the simulator runs on a kind of averaging of prior simulations. It remembers them, and that's the problem. It's trying to create consistency where there isn't any. Oh, I should get rid of these numbers. Which one is it? There we go. All right, so let's do some more. Oh, look, it's an arch. Oh my God, that's backwards damp. See? Look, oh my God, it went up. Now we're getting somewhere. That's a good sign. That's a very good sign. Any further, because it's not going to tell me anything. That's a very good sign. So it is a quantity that counts. Oh wait, I don't need to do that. I just do that. It's already stored in memory. There you go. So how many is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, just like before. Oh my God. So 9 is the minimum. So, just like Byron's. How about that? Let's see. Where do I put this now? Do 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 do. Oh, Susanna, why don't you cry for me? I come from Alabama with my banjee in me knee. It's my version. When I was a kid, I made up. All right. Now what? Engaging 4 additional. Well, it's more like 1. Engaging 1. Additional ground. All right, so this okay, get rid of that. Get rid of this. Get rid of this. There you go. So that's the magic. Now I have to change the well, no, it's probably better to keep it. Well, okay, so if I take it off, oh, it's not as high as before. Let's do that again. It is better to, so what was it? It was e to the 4. Yeah, you get better results, I think. 200 Gs? Let's try that again. I have such short-term memory. 200 Gs. Get better results when you take a longer view. Usually is better. How about e to the 3? No, it was better the other way. How about e to the 5? E to the 4 is the magic values. So you get different cutoff points, different instabilities. Now what we do is we zoom in. So in order to see what we're doing, we change the scale. We make this 0. And then, oh wait. Gotta find out where the cutoff is. So the cutoff is at 1.8 thousand seconds. So if I cut it off at 2000, let's see, let's go back to Tera. At 2000. So that would be 2K. So I make 2K here. And there it is. So now I have to go down here and wipe out all of these. I can either put 0 there or just delete it. And that'll help put scales on all of these instead of just the top one. It'll recompute the scale division. So I guess I'm giving you a tutorial on how to run this thing. Now for some reason, the energy doesn't start computing until here, or it doesn't show up. See, there's the ticket. So let's go to here. And so it's had a low value of 0. Well, let's create the same value as that. For starters, I guess. So negative. No, it's hovering out there in the middle of space. How weird. Alright, whatever. You want it to be 0, it'll be 0. So that's pretty interesting. So let's see, the power is oscillating. It can't make up its mind which way it wants to go. So that means that actually the negative is greater than the positive, so it's actually generating. So the caps and coils are generating power because we've got a negative here that's even larger than the positive side of the midline. The energy, I would assume, looks like it's an RMS because they took away the oscillation. So that's the other thing. It's not a strict division. It seems to be an absolute value. Or it may be an RMS. Actually, as I recall, I think that's what they defined energy as, is a kind of an RMS, and a kind of averaging over time. So it's not just, it doesn't just show you a positive, negative. Huh? What? Wait a minute, that doesn't make sense. No, look, the power storage is negative while the energy is positive. That's right. It's the caps and coils, the storage of energy in the caps and coils is generating power. So I guess what that means is what? Nothing. See, it's purely arbitrary. When they call it storage, that's a prejudice. They're simply categorizing all caps and coils as storage units, storage components, and so they call it storage. But now we're using it as a generator because it's negative, because the current reversal is taking place per duty cycle, per oscillation, per cycle of oscillation, and that means overall, in the course of multiple cycles of oscillation, namely the overall duration, we're getting power generation, even though they call it storage. They expect to call it storage. They expect that's all caps and coils are good for, is storing reactive power. But here we are generating power because, see, the conventional wisdom says that you have to have a voltage source or a current source or something similar to generate power, which is not really generation anyway. It's merely conversion of power from the format of power of the prime mover that's imposing itself upon the voltage source to convert into electrical power to supply the circuit. So you could say that a voltage source, a conventional voltage source, is a portal between the prime mover and the circuit, because it's converting chemical energy or mechanical energy from the prime mover into, or solar energy into the electrical energy of the circuit. But we're using it as a portal to do conversion between the inner space, the counter space, the imaginary field, the reactive field, and the real field, the real space, the outer space. So you could call it a conversion. It's a conversion device. So we've turned the coils and caps into conversion devices to convert from the ether, if we want to use the old nomenclature, into power. There you go. And so when we look at dissipation, it's the normal thermodynamic. It always seems to do that because they're using non-reactive components for their total power assessment and total and the derivative of that, the total energy assessment. So again, it's a prejudgment. It's a prejudice. So they're simply categorizing all resistive elements, prejudicially labeling them as dissipation, how much dissipation is occurring, because they assume it'll always be zero power factor. And it is zero power factor. It's totally synchronous current with voltage, and we get the same sign value between the power versus the energy. Then we look at the load. The load is negative watts. Not much, it's in the milli, but it's generating negative watts. And it looks like the V is much higher than the I. So during this explosive experience, I keep forgetting to do the, all right, we have to look at the, where should we put it? Let's make that the last. Let's save this first. Oh, neon bulb. Let's just check. Neon bulb. Let's just copy it. Control C, because that's the only way you can do that. Okay. And now we go. Okay, so then we put this. Actually, I want voltage, but that's okay. So we go, bring that down. We'll make it blue, because it's, well, no, blue is the right, because it's the voltage. And now that's the 7th window. Now, the voltage of the neon bulb, see, neon bulb, there it is. But we want a node, and it's called node number 10, which tells us whether or not it's on at the time that it ran. Now we've got to come down here, change our scope to be 2. That helps. Oh, it looks like it did not come on. Oh, very interesting. Oh, now we gotta go do that again. Wasn't paying attention. Okay, scales. See, what did we decide? 2000? 2K. Yeah, it's nano. So it's off. Yet it's exploding. No, it's going down. Whoa, I don't know which one is after the other one. Alright, I gotta change all of these now. Sorry. Gotta waste your time watching me do this. Well, maybe you don't have anything better to do. Why not? Well, no, you might as well get the routine. See, there's the routine. You get to know the routine, then you know how to deal with the simulator. Then maybe you too can become a simulator operator. Simulation operator. Alright, so now we got scales and everything. I don't know if I like the colors. So this is, so now we want to I think I want to save this. So I'll save the output, export graphic file, and it goes to Bobby. Where's Bobby? There you go. Do you like that, Bobby? Is that was your nickname when you were a kid? Let's see. 10 grounding rods? Not anymore. Uh-oh. Shit. Damn it. I ought to get a rope and hang it from the highest tree. I forgot how many grounding rods there are. Well, I'll have to change it later. That's no good. Alright. Is that ping? Yeah, that's ping. Okay. So, now let's see. What was the thing? Oh, I want to find out the numbers. So we do a numbers graph. Now, let's see. What I want to see... I want to put the left one on high. Where's the high one? It went to low. Which one is that? Oh, wrong one. And then I want to put the left one on the low. Well, it's still 10. Yeah, it doesn't give us... Well, no, wait a minute. No, yeah, it's too slight a yeah. So there is a difference there. Oh, but is the 10... yeah, it's pretty much at the same time. Oh, that didn't help. Well, I'll tell ya. So we get all this power that's happening, but not at the load where we want it. Well, that's no good. Well, gee whiz, Mr. B. This ain't very good. Maybe we should add another grounding rod. Dearie, dearie, dear. That looks better. Why did I think it was worse? The wattage is better too. Oh, and you see, now the, so it is. The thing is flashing on. Well, let's add another one just to see what happens. It is so much fun. No, it's gone back to it can't make up its mind. Alright, so we'll stick with the other one then. So 10 grounding rods seems to be, but the break is still here. In fact, I can check. Yeah, it goes back to the off condition. So it seems to be enhanced with that extra grounding pair. So it's actually engaging 2 additional grounds. Fine with me, I don't mind. Whoopsies. Then we need another arrow. Oh no, I lost my other one. No problem, Mr. B. We'll just move it, copy it, and move it. There we go. So we go back to running the thing. So let's see. So we make this 2000. So what I'm seeing here now is the tendency not to oscillate but to go up. So I think that's what's happening. The neon bulb is turning on. Even though it doesn't show us any change of voltage across the neon bulb in that position of the neon bulb. So let me finish what I'm doing here and then I'll show you what I mean. Because neon bulbs in microcap are very interesting. They're actually a slightly complex circuit to simulate the behavior of a neon bulb, because a neon bulb is a very special component, very complicated personality. Alright, so now we got our scales, and then we can Save it. And where are you? So, oh, that was my output? Well, that's not... Wait a minute, wait a minute. I keep forgetting, oh my god. You know what? I'm going to do this. Do it right. Oh, now it's 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm back to 10 again. The magic number. I could have kept what I had. Oh my gosh. Redo it. How many times I have to redo things? 2K. 0. Alright. 0. 0. 0. 0. 0. 0. Okay, now we get to save it. But this time, where are you? This time, we say output graphic. Whoopsies. Right, so we make output graphic. And then we do, which one should we do? Well, I guess up here it is the best one, huh? Oh, now they're not generating. Well, that's strange. They were before on 9, but we still get a... Huh. I guess it is at the terminus, because that's... It all matters when you take the reading. So if I do this here, it's 0. The energy is 0. Oh, because it didn't start yet. It started to compute here. It's not generating anymore. So where's the power coming from? I don't know. Oh, that's interesting. That's never happened before. Whatever. Oh, let's see, Bob French. Output numeric. Oh, dear many. Alright, now we'll go pick up the voltage nodes, the nodal voltage. Oh my god, look how low. Oh no, see, it's high. So the Earth is not going to be, it's not going to have a whole lot of end result nodal voltages, but it may end up getting a large dissipation. We'll have to see what the power is. Yeah, see, so the load doesn't have a whole lot of voltage difference. It's got nearly 200 millivolts on the ground side of the load and nearly 16 volts on the circuit side. So that's why that's probably not the best place to put the load. There's probably some other place that's more advantageous. But that ground I wonder if it needs to be there. Ooh. Oh. What would happen if we drew it back to here like it was before? Wasn't that the way it was before? Yeah. Tie the load back to here. Well, that's not hard to do. If I do Control W, and then, let's see, take away this, bring this up. T will make this, I don't know, a short, a switch, the load switch. The load switch should be red. Alright, so then we take this, and we put it here. And that should be interesting, since there's so little power on that thing. That was it. No. No, that didn't do any good. Shoot. It made it worse. Okay, so that prior arrangement doesn't work. So it's the wrong place for the load. That's basically the bottom line here. Oh, I see. There's a line here. So I don't know. Oh, we have a fuse there. Duh. Maybe the fuse is getting in the way. Do you think? You think? No. Funny, I overlooked that. That's a little better. Now we got 12 watts. No. 200. Oh, I see. Like 100 watts. 50. No, 100. Yeah, 100 watts. Oh, so the current was too low. Oh, now it's E15. The power level on this thing is even higher. Oh my gosh. So you see there's a lot of room, wiggle room for playing around with this thing. Well, let's see. If I shrink this down and I look to see where is the best place to put, I gotta put my glasses on. Where's the greatest voltage difference? We got Terra, we got oh, the neon bulb. Yeah, it's beginning to come on, but it's not really on yet. Well, it seems to be down in Terra, 99. Oh, the transformers are doing very nicely. So all of, ooh. Oh, it's all here around. You're going to blow the transistor. That's for sure. Oh, it's on the left-hand side of the very first transformer. So this inductive ballast, maybe I should be looking at that. Chanté, but it's not much. Oh, maybe that should be the load. Okay. So, let's take a look at the inductive ballast. All right. Now I got that figured out. I can take off my glasses. And change No, that didn't help. It's not enough voltage difference. Yeah, because they're practically the same. So even though the voltage differences are high here, it's not a place to put a load. We need voltage difference, which means down in here somewhere. These adjustment caps, that's a big difference right there. So we should take a reading of the adjustment cap. Or the ground cap could be a load, a capacitive load. Yeah, yeah. So either... Oh no, wait a minute. The node up here is practically the same as down here. So actually it's the ground cap where all the voltage difference is happening, is one way to look at it. The other way to look at it is to say that this first transformer, humongous amount of voltage on one side versus on the other side by a huge factor. So that's the second place. So this first transformer is acting like a very auspicious load because it has such vast voltage differences between the two sides. And this ground cap. So you have two possible loads, capacitive and an inductive load. So if you use the magnetic field here, well, what's the current? Let's see, where's the current button? Oh, the current's not very high. It's all voltages. This is a voltage multiplier circuit. There's not a whole lot of current going on. So it's strictly voltages for the most part. Let's see, anything hot? No, wait a minute. Off, 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 off. Hot. Ah, so these two are hot. Well, that would mean the current is running high. Let's see, where are we here? Huh. Or the current is trying to go in reverse. Very forcefully, maybe. No? They're just hot. Okay. Well, you can light them up. If they're LEDs, they'll light up very nicely. And it's these four. Because they're the only ones that are hot. In fact, all the others are off. Interesting. So let's see. So I can't... It looks like the ground cap is the one to do. All right. So let's change that. GNDCAP. Uh-oh. My poor eyesight. There we go. Darn it. Yeah, it looks right. What did I do wrong? Oh, I see. I need new glasses. Ah, there we go. Yes, 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 Tara. It's all on the ground cap. So the ground cap, let's see, is a very small. Let's see if we can increase it, because it's not going to hold much charge. Get away with increasing it to... What's going on here? Capacitance. What the... Plus... Oh, that is... Oh, it's a holdover from what I did before. No, that's okay. Let's make it 100,000. No, I think it's 10,000 is the highest. Oh, that killed it. Oh, that's one way to kill this, the over unity. La-di-da, huh? That's another way to kill it. Let's see, it was 100 femtos. So if I make it a pico, why did it... Oh, it came down to 0. Tera, it's still Tera, that's pretty good. So, gee, what's the limit here? Pn, 1n? Oh, so it's a throttle. It's bringing down the... Oh, wait. Oh, it killed it. It's more than a throttle. It's another type of switch. Oh, see? That's a definite transient. Surge in the beginning. And yeah, well, it's stabilizing the surge. So the other... So we don't... Maybe this is just a transient condition. So that's 1 nano. 100 pico. No, that killed it. $10 pico. So, ooh, 23, that's pretty good. Wow. So it doesn't have to, it's, well, it is what it is. What can you do? Let's see if I can raise it up anymore. 30. So it's raising before it collapses, which... Yeah. So if I raise it to 70... Oh, so there's no way of knowing what you can do. How do you like that? I tried 100 already. So I think I'm going to leave it. Oh, look at the neon bulb. It came on. Oh, it stabilized the simulation runtime. I bet it's longer now. Sorry for screaming. Oh, yeah, instead of 2,000, now it's over 11,000. Cool. So it's stabilized. So raising that cap helped the simulator do its job, which means it's less stressful for the circuit. Whatever's less stressful for the simulator is less stressful for the circuit. So it raised up to 10 volts here, which means the neon bulb came on. So that shows that regulator is where the over unity is coming from. Now, the power gain, wait a minute. Now the dissipation is now the diodes are generating power. Yeah, look at that. Because the power is negative and the energy is positive. So now it's the diodes that are generating energy. Wow. Cool. I like this. Um, 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 um. Whoa. Let's see. Kill that. Then we'll come in here. How do you like that? How do you think about that? So, 12K maybe? Let's see if that does the job. Yeah, kind of does the job. Although, is it 12K or is it 11? Ooh, that's a little tight. I should stick with 12. It'll be better. Nice whole number. All right. So now I just come down here and wipe all of these out. Oh, this is good I did this. So in a sense it's a throttle because but in a sense it's an on-off switch. So it's another way to turn this thing off. This is so cool. Oh, this is so cool. I love it when I get big numbers. So you see this goes up to 10. These are divisions of, what is that? 6, 3. So divisions of 3. So this must be 12, and this is slightly more than 9. So that makes it, yeah, that's probably 10. So we'll take the power, or the graphic. And where's the graphic? And then we do the, all right, so I want to know the power, so we come down here to the power level. So before the surge begins, it's at 365,000 watts, but when it terminates, it's when the simulator terminates, it's 1.863 gigawatts and climbing. That's a pretty good S. And see here, if we look at this value down here, this is 10. So, it's 10. Oh, well, see, it's 10 nano. It shows that it's off. So at the base of the surge, when the surge first starts off, when the explosion first begins, the spark gap is off. But at the end of the simulation, when it's in the midst of this explosion, the spark gap is on because it's 10 volts. And that's what I use that. Oh, I haven't shown you that. I'm going to have to show that to you. I keep forgetting all the things I need to do. So let's see. I need to save this as the numeric. And then what do we have? Do we have anything negative? Yes. So we have negative power and positive energy, and that's the dissipation. So it's probably the diodes that are generating it. And that's what happened with Byron's circuit. So that's what you do with a voltage multiplier. The diodes are generating the over unity, I guess, creating the possibility for the raise of voltage, but it's not over unity because nobody thinks about using the earth, multiple grounding rods to throw away the voltage source and truly be over unity because you don't have to pay for it, right? It's all for free. It's like solar panels. It's all for free, except you're getting it from the earth. So in the middle of the night on a cloudy day, you got power. How much better is that? Oh, that'll put the solar energy business out of business. And the wind farms, when the wind's not blowing, what are they going to do? You got yourself a renewable source of energy. Oh my God. You guys could make a fortune off of this. I know, Bob, you kept saying, well, we're not going to make any money off of this. Well, I don't know. If you do it through grassroots, spreading it around, not try to go public. So you do a copyright. You don't do a trademark, and you don't do a well, you could do a trademark just for the logo or whatever, the image, but you're right, for the but for you don't do a patent because you won't run the risk of having it sequestered out of public view and made highly classified. So you do a copyright, um, which you still would have to go through government unless you simply do like a self-publishing, but then it's a limited copyright. It's a limited ISBN number for your text. So that's why I've gone this route, because Byron kept telling me, do copyright, because that's what he did on his circuit, his hairpin circuit. He copyrighted it with the Copyright Office. So I don't know what kind of risk there is, because they don't, I don't know if it's already been copyrighted. But you don't do a patent, because patent costs too much, takes too long, you have to run through attorneys, so this way it cuts your attorney cost. Anyway, yeah, everybody does patents for industrialization, but for copyright, trumps. Byron said, copyright trumps patent when it comes down to a legal court battle. Who has the last word on the subject? So, anyway, according to Byron. Byron Brubaker. I don't know, could be true. Now, we wanted to get rid of this. Now, I don't have a text here yet, but that's okay. I'll change it later. I'll modify it. I'll put text along here telling me what the ground cap is, which is 70 picofarads. Now, I don't have any fuses, but I can't take that away because it'll change my volt. Oh, why don't I change it? Come on. Don't be a sis. Well, I may want to use fuses later on. Could be. Okay. Yeah, why don't we just do this? So here's the voltage readings in the gigavolt range. Well, that's better than what it used to be. Yeah, it's kind of useful to know where the high voltages are relative to the low voltages, because then you know what you're dealing with. So, and then we do the current Whoa! Where'd all that current come from? It's not on the grounding rods, makes sense, but look at all the current. I've never seen so much current before. Holy cow! And it's drawing current in from here, and it's drawing current in from here. So now that I raise this cap, it really helps the circuit function better. So it's actually drawing in power from the ground. Maybe. We'll see about that. Let's see. The diodes. You have to do a wattage thing of each diode. That's the best way to do it. Yeah, right. The individual diodes. I haven't done that. So I'm going to try that. Ooh, that'll be good. So let's see. Let's get this reading first. I hope I'm not going to destroy my hard drive. Well, I lowered the clarity of, because my simulator or my screencaster wasn't working very well. So let's see. This is current pathways. And then we do energy storage. Oh my God, look at the energy storage and dissipation is humongous. The Earth is not getting a whole lot of anything. It's getting some dissipation, but very little, so we don't have to worry about impacting the Earth in any kind of adverse fashion, except for here. Here is very high at the so-called load. Oh, that's a good question. Is the load actually a load anymore? Oh, I forgot to check. Darn it. Oh God, I gotta reevaluate. Well, I have to reevaluate everything anyway. Let's see. This is, what is this called? Power. This is called power and energy. Oh, total power. Power, total power. Okay. Then with the condition of the diodes. Oh, look at this. They're hot. Ooh. They're all hot. Hey, so before I raised that ground cap, I wasn't fully making use of these diodes. At least from the simulator's point of view, of course. You know, but by letting it run longer, by encouraging it to run longer, by allowing it, facilitating it to run longer, we get to find out what's really going on during the explosive process. Let's see, what is this? Condition, whoops, of diodes. Condition of diodes. Right, okay, so that's that. So what was I going to do? I was going to add on the inductive load. Where is this? So the ground, well, everything was high. That is for sure. Oh, let's see. No, it's this one. All right. So this becomes 6, 7, 8, 9. And a little longer. And that happens when you bring in other values to compute. It'll change the way it behaves. You know, these simulators are really touchy in how they function. They are really weird. And I have to put up with it. Alright, so now I get nice deep lines. Oh, is it the right colors? No. Well, gee whiz, gosh, Mr. B. Colors. So that was watts. The grounding cap was watts. I can make this green. Oh, wait a minute. Everything's backwards. That's not green, that's black. I'm comparing the two wattages. Oh. So this should be green. Hmm, it was nicer before. Oh, I see. So the inductive load has more power, e to the 20, than the ground cap load is only giga. And that makes sense because it's a tiny little cap. So the inductive load has gone back to becoming a load. How do you like that? Let's see, the inductive load, very high voltage, so it's not going to have a whole lot of current on there, so maybe it should be a capacitive load. Yeah, that might be better. Right. Okay. Let's try that. Let's see. Which one is this? No, I'll just do C. Let's see, C. Here we go. So, now it's not an earth cap. It's, what are we going to make it? How about, 1K? What would be a good... We could just make it 1. Alright. But we got to do it this way. We got to put in and then random string of numbers to give it a unique identity. So I found that all of my reactive components, such as caps and coils, I have to give them unique identities, each single one. Although I don't always do that. But I try to do it as much as possible because it helps the simulator run more efficiently, which means it runs for a longer duration. Now, if that's a load, well, I could try 3, I guess. 3 ohms of equivalent series resistance. And let's see where the poles are so I know where it is. Oopsie. So now I know the plus is on the bottom, so I have to rotate this. Oh yeah, that'll work. Okay. That's tend to see where I want to put it. So now I got to take out this. So it's 1 farad. Oopsies. Take out the pin name. I always try to keep the positive pointing. So all of these caps, the positive terminal points towards the circuit so that when I get the readout, then I know what orientation I'm dealing with. So now this becomes the capacitive, whoopsie, load. And this is, what was it? 1 farad. 1 farad. 3 ohms. 3 ohms ESR. And we'll make this red. There. So now I got a cap load. Now we got to save this as a different file. 10 grounding rods with diode. And cap load. Alright, so now we... Oh, wait. I have to say what this is. So I'll copy this. And that was 70p. But how much resistance? 3. So everything's 3. I don't think I have anything that's 10. Right. So all the caps have equivalent series resistance of 3 ohms. Oh, that's okay the way it is. Okay. Then this one goes down here. The ground cap equals, what was it, 70 picofarads, and well, that's good enough. There. Oh, I don't need that. I can just say there. Or I can put it underneath here. No, that's too crowded. See, I hate it when it does that. it's called snap. It tries to snap it on the corner there. There we go. So this is now with a cap load. So now instead of an inductive load, well, actually, this one should go up. There we go. So now instead of an 1, 2, 3, 4, 5, 6. So now instead of an inductive load, a little lower power by putting a different load there, but it makes sense because look, the E to the 15, no wait, that's the ground. Oh, Terra, shit. So the ratio between voltage and current is very high. And of course you'd want a capacitor there. Wait a minute, this is the load. Yeah. Oh, I got the wrong colors. Oh, I have the wrong color schemes. Maybe I should do it in different colors. Let's see. The ground cap, we don't have to know what it is, so let's make that green. In fact, well, no. Let's make this blue. And this black. And this red. So let's see, now it's stopping at 13,000, so we'll make it 14,000 seconds. So it runs a little longer. See, this is the blue one. $14K 0. Yeah, perfect. Ooh, see? The neon bulb came on. And it ran for a certain length at 10 volts. And that's where we get our first spike on the load. So the cap now is exhibiting spikes. And that's why the power is going up. And I guess I'd expect that of a cap. Nothing smooth about a cap. I mean, it does a little something here, but then it drops back down, and then it spikes in the negative direction. So the cap now is exhibiting negative watts. Negative watt spikes. How do you like that? Interesting. I'll delete it. See, it works just as well because you go back and I put a 0 there. But we'll put a 0, whatever. Whoopsies. Wow. Cool. So we're still getting the same power gain, more or less, before the thing shuts off. Now it's shutting off because the time interval keeps shrinking because the energy gain per unit time is increasing. So it's accelerating. It's escalating its power gain, which means it's exploding even faster than before. That might be why this is a straight line here. This is the power that's being dissipated. And this becomes a straight line, but this was a nice curve before that. So it shows it's accelerating its escalation over time. And that's why the simulator gives up. So what is this now? With neon bulb. Oh, this is a different cap load. Oh, I see. It's already different. So I'll copy that. So this first graphic is output graphic. Whoopsies. I don't like caps on my extension here. So there's my cap load graphic. And then we come in and do a numeric. Let's see. If I want to look at the spikes, then I want the lowest value on the left. Whoa, that didn't work. Oh no, not the lowest. The lowest value on the right. There we go. And then keep doing low, low. Did I miss it? Oh yeah, I went right by it. I wasn't even paying attention to what I was doing. Huh. So what I could do is bring it down to here. And there. And then I just transfer it up to here. And do shoot. Oh, I wasn't supposed to do it that way, darn it. So I hit this, no, I hit this, and then I come up here, and I go down. So that was negative 181, negative 428. No, it's still not the lowest. Oh, negative 2000. Ooh. 2069. Oh, now it's going back up again. 2069. Huh. Back up to there again. And then we go to here. Oh no, that's the high, the lowest, 21414. So the spike goes as far as negative 2000 on the first spike, and the second spike is negative 4000. But these are what am I looking at? Why is that? Is that division? Oh no, I have the wrong color scheme again? Wait a minute, what am I doing here? Ground cap? I have the wrong color scheme. Oh, I can be really dorky sometimes. Oh, this is nothing. Oh no, there's no power there. All because I had the wrong color scheme. I'm looking at the wrong thing. So a cap load doesn't work. I had better results with an inductive load. How can that be? All because I had the wrong color scheme. Throw you off every time. Yeah, and my poor eyes. No, this says cap load. Why do I... Wait a minute. Oh, I made this green because I wanted to avoid that. Even though it's very high, but it's not something we can use. Oh, that's funny. Oh, it has a bigger spike at the end. Oh, I see. I was just looking at these spikes here. Oh dear. It's so bizarre. Did I save it already? I don't think so. I do not think I did that. What do we got? Output graphic. Oh, I did save it, just not the numeric. Yeah. Oh well, whatever. I gotta go through that all over again. Or do I? Yep. I blew it. Wait a minute. We come here. And we do that. And then we do here. And then what did I do again? I took it down. There, that was the highest value. So now I can save it. And it's numeric. All right. What was the other thing? Oh. So in the beginning, it looks like the caps and coils are generating power. And at the end, no, excuse me, the first spike. So the first spike, the caps and coils are generating power, and they are dissipating in the normal manner, as they normally would. But that's the... Oh, I'm sorry, no. The first spike, the caps and coils are generating power, but the diodes and resistors are dissipating in the normal thermodynamic manner. Yet, the capacitor on the first spike is generating power. It's because it's negative 2,000 watts. On the second spike, the caps and coils are generally, as a total, because up here these are total values of the whole bunch of caps and coils, are storing power in the normal thermodynamic manner. So nothing wrong with that. And they're dissipating, the diodes and resistors are dissipating in the normal manner. So I must have caught it at a bad time. Meanwhile, the capacitive load is still showing evidence of negative watts. It's hard to imagine that a capacitor could generate power. Well, but see, it's the foundation is this the neon bulb turning on. So I don't know how to... Well, let's see. Let's get out of here. So let's do a schematic. I haven't done a schematic yet of the other one. Let's see, schematic. Then we'll do the voltage. Tera. Ooh, tera. Teravolts, very high. So we'll do nodal voltage. Funny, my computer hasn't warned me yet that I'm running out of disk space. nodal voltages, and then the current. Oh, the current is very low, much lower than before. So it's actually safer to run this version. How do you like that? Let's see. Alt E gives me there, and then I have to go into there. And so this is the current pathways. And then, yeah, the total power is small. That makes sense. Total power is small everywhere. Well, that's slightly elevated. It's being dissipated like 200 watts. Yeah, but you can't dissipate it in a cap. No, but it is. See? PD, 185. So if you hover over the component, it'll give you the PD. It says the current was almost 8 amps, while the voltage was 1300 volts. The last value was, the voltage was 80 volts. Huh? How can you have two last values? Power terms. Power storage 0. Huh? Power storage 0. Go figure. Whatever. Don't expect me to understand what I'm looking at. Let's see. What is this? This is the, what's it called? The, total power? No. Component powers. Individual powers. I have to change that on the other one. Let's see. And, ooh, look at this. Now it's, those two diodes are turned off, and these have remained on, so it kind of varies. Well, the capacitor, yeah, because it's a capacitive load. So it took some of the strain off of the diodes, I guess. Alright, so what was the thing I was going to do? I don't know. Well, now I'll just... Oh, fuses. I never put any fuses in. That would be interesting. Where do I take a guess, estimate, where to put the fuses? You know, the cap load, I bet you'd have more power if it was reduced. Yeah, not a super cap. What was the, let's see, what was the output? Cap load, output graphic. So, what am I looking at? The watts? Oh, in the 1000 range. Yeah. So, if we change that to reduce it down to oh, it changed it. How about that? Alright. Made a whole number. Let's see, the next one down would be milli. So let's see, millifarads. So that's 1 millifarad. The power level is humongous, giga. It grew in a substantial way. Okay, so if it's milli, then let's try 10 milli. So if that was milli, 1 milli. So if I make it U, 100 microfarads, now it's in the negative direction. It's about the same. So you've got a range between 100 microfarads and 1 millifarad. The fact that the capacitor is negative watts, though, in this instance, well, it was in the other one, too. As well, I mean. Oh, I see where I made my mistake. I'm not measuring. Well, that's not very swift of me. Why is that different? Ground cap times cap load. Oh, this thing really is mixed up. What? Cap load. Why is it giving me? Oh, oh no! I really am mixed up. My color scheme is totally mixed up. I gotta change my color scheme. There's no question about it. I am all messed up because my color scheme is messed up. I'm misunderstanding. So these are both okay. So this one, the ground cap, has to go up. In fact, maybe I should get rid of the ground caps. Yeah, probably. Alright, I'll turn that off. The ground caps. So you got times, divide. This should be green. And this should be blue. I'm reading the wrong graphs. There we go. Cap load is going up here at 4. Okay, so what was so that's 4, or almost 4. So what was the value? This is 100 micro, 10 milli. Oh, it's like nothing. See, if your color scheme is off. So that's 10 milli. And that's 1 milli. Best results is when it's 100 micros. So what if it's 10 micro? Let's see. So 100 micro looks really good. So that's not bad, 100 microfarads. So let's put that in here. 0, 0. I don't get to use a omega, but at least I get to use a micron symbol. Let's see. That looks good. And then the time is around 11,000. So that's not good. I guess 11 is not good. Huh? Gee, I don't know what I'm doing. Oh, darn it. 20K? Okay, what is that? 14. That looks like 15K. 15K. Yeah, looks pretty good. Okay. Oh, the bottom one. Oh. Alright, so that's now the best. Oh, okay. Oh, yeah, I get more power on the load and less on the total quantities, so it's being distributed differently. That's what's happened here. So where's the graphic? And then the numeric. Oh, I don't have to adjust anything. So now the wattage on the cap load is not negative. Yeah, everything at those positions, everything looks like it's normal dissipation. But I'm sure it's going in reverse at some other points in time. Output, numeric. So then we take this away, and we do a schematic. Where's the schematic? And we do voltage. So it's 500 volts on one side of the cap, but 26 megavolts on the other side of the cap load. Meanwhile, we got tera here, mega throughout there. Ooh, we got tera here, above the adjustment cap. Yeah, it's pretty high. Oh, well, yeah, that's, of course, a voltage difference on the cap load. It's what I want, right? Let's see. What is this? Nodal voltages? Nodal voltages. And then the current pathways. So this was kind of fun, developing this. Fine-tuning it, current. Power. I want to double check that inductive load. What's this one? Power. Where is the power? Individual powers. What? It's not going to... What did I just do? Oh, wrong one. And the diode condition is probably the same as before. Diode condition, where are you? Conditions of the diodes. And I think that was it. So let's go see what we got. So the output graphic for the cap load is for it's 3,000. No, excuse me, 3 gigawatts on the cap load. Not bad. Meanwhile, where is it? I don't have it. What? What happened to it? I never saved it? What happened to it? Wait a minute, don't panic. Don't panic. I'm panicking. I never did a graphic, but I did save the circuit, didn't I? So there's the cap load. Oh, this should be the inductive load, shouldn't it? Right. Oh, dear. That's the problem. Gotta rename it. Now what happened? Oh, whatever. Alright, now I get to find out what goes on here. Well, I never measure it. Well, there's my problem. I did. I see. I didn't save it. That was my mistake. I never made a screenshot, so I can't even remember what I did. Boy, doesn't that sound familiar. Now let's see if I can get the color schemes correct. So the ground cap was here. Move up. Move up. The inductive load, the ground cap, keep it as green. Oh, these are the right colors. Now I gotta just go to the right panel numbers. Or tracing numbers, whatever they're called. Alright, so that should work. Inductive load. Okay. Just the lines will have to be strengthened. These two. Oh, wow, it's higher. Oh, wow, the power's better with using an inductive load. See? You never know what you're going to find out. So much for using a capacitive load. Look at me. Famous line from a movie. Okay. So, 11,003. 11,003. That's weird. Okay. What am I looking at? Yeah. Alright. 11,000 and 3. So that means I could do 1, 0, 0. There we go. 11,100. Okay, now we get to do the power, or the graphic. Now, to do this the easy way, I look for this one. Oopsies. Cap load. Inductive load. And then the numbers. Where's the numbers? You. Alright, so. Oh yeah, this, no. Oh no, right. The dissipation. So the diodes are generating power, because it's negative. Negative, positive. Negative time interval. Wow. So, oh, I was supposed to look at that. The wattage on the inductive load is not negative. Yeah, I was supposed to look at that. Alright. I gotta do another one. Well, no. One thing at a... No, I should. Oh, darn. Which one do you think it is? Oh, I don't know. Well, let's just do this. Output graphic. Output numeric. Alright. Which diode? How about... Which one is this? Diode number 1? That's diode number 1. So I'll just take all the diodes in sequence, I guess. This was 2, this was 3. This one is 8. Was there another one somewhere? No, 8. So 1, 2. Oh yeah, and then it goes to the left, or to the right, I mean. Yeah. So 8 is the last one, and this is the first one. So what are we doing? We're going to look at the voltage and the current. The voltage of diode number 1. The current. That would be blue and red. Oh, they're both positive. So let's see. Oh no, I shouldn't do it that way. I should do it this way. Properties. Okay. Let's go out of here. Save it. Now, instead of D1, let's try D2. Which, again, doesn't help. Be interesting to find out. It can't be a resistor, that's for sure. Nope, both negative. How about number 8? Well, let's just do it methodically here. It's always a good idea to not lose track of anything. So that's not anything. This is what, 4, so we go to 5. Oh, it's a little higher or lower. 6, 7. Wait a minute. I didn't do the right one. Oh, ha ha ha. Getting ahead of myself. Yeah, I don't know how else it could be that it... Well, not in this instance, that's true. It may not be. Wait! Huh? No, they're both going the same direction, yeah. So it's not the diodes. And yet it claims it's... There must be some other dissipative element that it's... Oh, there was one other last thing I wanted to show you. So let's get rid of the diodes. That's a waste of time. Okay. So, microcap macro for its neon bulb. Library. Spark gap. So I'm going to include this when I send you all of these files. So this is the macro. So this is the circuit pretty much in here. These are the two terminals, or pins they call them, of the spark gap. And it's got two capacitances. It's got the inductance of the electrodes combined into one. It's got a negative resistor here of -1 ohms. It's got two diodes facing back to back. It's got a current source, which is manipulated by these components here. These are digital logic components. It's got a voltage source of 0 volts, and I think that's for the purposes of measuring, what is it, current at that location. And then it's got this switch check. So the alternate name for node number 10 is switch check. And that tells you whether or not it's switched on or not. Switch check has too many characters. I just remember the number 10. Node number 10. So if we go and look at nodes, see? Node number 10. So I just use the node number rather than the label that's pinned there. And that tells me whether or not it's on because of this expression based on the voltage. If the voltage goes above the threshold, 90 volts, then it tells this to be 10 volts. But if it's below the threshold, this statement here, this voltage source, this behavioral voltage source, becomes, so what was it? When the threshold is below 90 volts, the voltage here supplied by this behavioral voltage source is 10 nanovolts. So and then it puts that here, because it has a little capacitor to store it. So this literally, and then this is carried over to here. Switch check. The current source looks at the difference between this node, the voltage difference between this node and pin number 2, and it multiplies it against the voltage of the switch check. So it's an interesting macro. So I made all kinds of modifications when I wanted to create a modified spark gap, but this is what the neon bulb spark gap looks like. And then I modified this to reflect what a helium spark gap would be, such as reducing the voltage threshold to, I think it's 54 volts. Anywho, so it's interesting. I'll include that in my package, my zip package that I send you. And this is the spark gap. Schematic. Pretty much. Let's see. So what's possible, what we can do, this is the cap load. Wait, what's the difference here? Oh, this is the cap load. So the cap load's not very interesting, so let's not focus on that. So this inductive load. So what I can do, since I've already set up the time frame for the analysis, for the general analysis, what we do is we can do a specific probe analysis and see what's happening inside of the spark gap. Just for the hell of it, just to show you what goes on. So I do probe transient now, and I let it run. Matrix is singular, and it coughs out of me. Darn it! So I forgot. I have to change it down. What did it cough out at 11,000 or 12,000 seconds? So let's see. If I make this 40. Oh shit. What was it? E to the 4 or e to the 5? Darn. Well, there's one way to do this. Is to close it, don't save it, and get it back again. And then go to probe analysis. No, go to analysis. Oh, e to the 4, that was it. So let's just do 1K. Oh, did you see what that looked like? Well, right here we got triangle waves, which is a good sign. But I saw triangle waves, I think it was here. Let's go back a bit. Let's go 100 seconds. The triangle waves on the watts of the load, and that's a very good sign. That shows that the inductive load cannot saturate. It refuses to saturate, and that's why we get infinite gain. Oh, see, it's a little different here. Always something different. Yeah, let's go back. Oh! Total power storage is a triangle waves. So isn't that interesting? 200 maybe. No, it starts to behave differently. Well, I guess 100 is the only way to go. How about 10? No. 100? But that doesn't look nice. Okay. So 10 seconds maybe. So it shows that, oh, even this. So it shows that there's no saturation anymore. And since this storage is on caps and coils, that includes the coils, it's when coils exhibit these triangle waves, I read this on the internet, it means that the coils refuse to saturate. And that means in this condition, anything goes. You can go at the sky's the limit if you've got an over-unity circuit. But see, that statement on the internet was predicated, I think, on the conventional wisdom that over-unity does not exist, blah, blah, blah. So they were not in fear of being, it was, I think, an electrical engineering website. But of course, from our standpoint, it interprets differently. The consequences interpret differently because this thing is going to go to infinite oblivion. So I'm going to save this and qualify it as, no, what's it doing? Whoopsie, wrong place. My fault. Okay. Inductive load. Oh, I didn't do all of the other schemes. whatever. Let's see, output graphic of the inductive load, and I specify that it's 10 seconds. 10 seconds of output. There. So I hope you enjoyed this. I'm going to terminate the video now, the screencast, and see how much space I took up on my hard drive. I forgot to do one thing. Where's my microphone? I forgot to do one thing, and that was to give you kind of a minor analysis of what's happening inside of the spark gap when it fires. Unfortunately, I could not find out what was happening inside of the spark gap when it fires when running the inductive load version. I could only do it when running the capacitive load version. So here's the macro again, and what I did was I took the voltages of the two capacitors and I graphed them separately or on one graph together, and then I took the current of the inductor L1 here, which represents L1, it represents the inductivity of the electrodes of the neon bulb, while the two capacitors represent the capacitances of the neon bulb when it is on versus when it is off. And so I took the voltages of both of those and the current of the electrode. And so this was the current of the electrode, and it's up here somewhere in the vicinity of 3.2 thousand amperes. So there's something like 3,000 amps going through the neon bulb when it's on. By comparison, when it's on, the voltage is somewhere in the vicinity of something similar. It's around the same value. So it's somewhere around 3,000 amps and 3,000 volts going through the neon bulb when it is flashing, when it is flashed on, when it's arcing on. That's all I wanted to say.
Please, 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 if you decide to take up the challenge of building any one of my circuits in which my convention is to do away with voltage sources altogether, please do not modify it in as much as do not be tempted to mix a voltage source along with my circuit topology, because my circuit topology is meant to be independent of a voltage source, and if you interfere with that by putting a voltage source in there, there is a possibility, not a probability, but a possibility that the negative impedance of my circuit will overwhelm your voltage source and blow it up before the circuit itself gets destroyed. And if you're using a battery, the battery may blow up in your face. And I will illustrate this with an example. Too often we think that impedance is a tragedy or what's a better word, a challenge that has to be overcome, and that's all it's good for. But what if an impedance becomes a big bully, and that big bully becomes your friend, and that big bully doesn't know any better, and he beats up your best friend because your best friend jokingly did something in your direction, and the big bodyguard, the big bully who has befriended you, and you've now hired him as your bodyguard, doesn't understand the relationship you have with your good friend, that it's okay that he makes jokes in your direction about you, like your hair looks funny or whatever, because he's your friend. But your bully turned into a bodyguard doesn't know this and beats up your best friend. Well, most people think that if they short out a battery with a piece of wire, that's the only way to blow up a battery. But I can envision a different way, and a mistake, an error of judgment, in which a person sees, well, there are so many resistances in the circuit, there's no way the battery could blow up. But if those impedances should become negative, they will have greater force to destroy and blow up that battery than a simple wire would have accomplished, because we are not accustomed to dealing with negative impedance, especially when the negative impedance is very large. And so we don't realize that a simple short of a piece of wire is wimpy by comparison to what negative impedance can accomplish. Negative impedance literally is having a bully for a bodyguard who will beat your best friend into a pulp if you're not careful. I mean this seriously, and I mean to use these analogies in a hurtful way, in a very serious manner, because well, I don't want to lose you. I don't want you to connect a battery thinking that, oh, well, we want to play it safe and not do Vinny's version. Oh, my version is going to blow up. But if you put a battery anywhere near there or in there, it's going to blow up the battery before the circuit blows up. I can guarantee that. Without even ever, well, no, because early on, that's what I did. I made the mistake because I didn't know. See, I was programmed the same as everybody else. Oh, you got to have a voltage source. Bullshit. If you put a negative impedance in your circuit that has a greater force than the voltage potential of your battery, the negative impedance will destroy, or any voltage source for that matter, the negative impedance will destroy the voltage source because it's more powerful. Because the absolute value magnitude of its impedance is already greater than the battery, and then you make it negative and it'll destroy it. Rather than be an obstacle for the battery to overcome, it'll be a bully that'll beat up your so-called, the battery is like your servant that you hire to come on a regular basis to clean up the house and doesn't realize you got a bully in there. And he may not know that you've got your housemaid coming once a week on Thursdays to straighten up, and he beats up the housemaid the minute she enters the building, your home. So this is the problem with negative impedance. It is a very powerful force when it's negative, despite the fact that the absolute value of that impedance may discourage person, or the person may misinterpret what that impedance could be capable of doing when it's negative, because everybody assumes nobody even thinks that an impedance can become negative anyway, let alone more powerful than the source that we're accustomed to using, like a big huge battery pack in a car. It could blow up. The circuit could destroy the battery pack before it destroys itself. What happens is the negative impedance pulls from the voltage source at a rate that is faster than a simple wire short would accomplish. That's why I brought up that for comparison. Literally, we think of voltage as a pushing, that it pushes current along, but a negative impedance, when coupled to a voltage source, will pull current out of that voltage source so fast that voltage source will become destroyed in an instant, long before the circuit becomes destroyed. That's how powerful negative impedance can be. It's a sucking action when affiliated with a voltage source. It will suck it dry so fast it'll destroy it. Because voltage sources nobody designed them with that in mind, because we don't live in a negative impedance world. We live in a world of positive impedances, and so we have this brain programming that we have to push against them using the force of the voltage force to push against positive impedances in our circuits to accomplish any kind of result. But I do the opposite, and consequently, caution must be exercised not to make a boo-boo. I mean, it's bad enough the circuit will blow up anyway from the negative impedance if not regulated, but having a voltage source is like adding alcohol to a fire. It's the worst thing you could possibly do is to make a mistake of thinking you're playing it safe and afraid to take the risk of going all out and giving up on voltage sources altogether and just depend on the negative impedance of the circuit alone to manifest energy. It's a mistake not to take the risk and let go completely. To go halfway is the worst thing a person could possibly do. Oh, I'll mix and match because I'm not sure it'll work out anyway, and I want to guarantee that I get results. And oh boy, you'll get results all right, and not what you bargained for. Oh, it's a sad, tragic fact, but someone's going to kill themselves doing any of my circuits. I'm certain of it. They won't follow directions. They never do. Well, never. I've only had one person in the past try to build my circuits, and nothing happened. But he didn't follow directions either. And he was working with circuits which I told him, well, I doubt they're realistic because it's, they're Paul Falstad's simulations, so I don't expect them to be realistic at all. But no, it's okay. And he went ahead anyway. So nothing blew up. He was expecting it to. He ran away from it the minute he hooked everything up, and of course nothing happened. But it won't always be so jovial or jocular. It may get tragically serious at some point when somebody makes a mistake in not following advice to the letter and trying to make changes. As Bedini says, don't make any changes the first time. Do it exactly the way I say. Later on you can make changes. And how many of us do that? I don't even do that. But at least I simulate, so if anything bad happens, I'm not hurt by it. But in the real world, it could be very dangerous. So that's basically what I had to say. Because all of my circuits nowadays, I start off by trying to do things conventionally your way because that's what you present to me. And so I look for all my options. And all that does is teach me what the circuit needs. It does not teach me how to give it to the circuit, the most efficient way to give it. And so this latest one of stacked transformers, I see it needs an impulse waveform from a voltage source. But lo and behold, I'm working today on a 3.5-hour video. It's taking me forever to edit, and it's boring as hell. But I thought I'd do one, nice and long, showing me going through all the different possible changes and whatnot of working this idea that I had, that you'll see what it is, in which I can do away with the voltage source altogether in your stacked transformer situation and still get it to explode with infinite power over a certain duration of time. It's not a bad duration. It's like a few seconds, or instead of, by comparison, it could be worse. It could be thousands or hundreds of seconds, but it's not bad. It's within a matter of a few seconds. It blows up to infinite oblivion. But I have no voltage source. This is very crucial, because this is where a safety flaw I have not bothered to mention to you. What could happen, what could go wrong if you mix and match first time off, thinking, oh, what a smart boy you are. I'll make the best of both worlds, conventional plus Vinny's weird way of doing things without any voltage source. But I'm so accustomed to avoiding a voltage source completely for the last, 5 years, that out of the 6 that I've been doing these simulations, that I don't even think twice to do any of my circuits, to start them out with a voltage source from the beginning. So I only do that because I'm coming from your world, and I haven't figured out your style of reasoning, that I haven't, and everybody else's, that I haven't yet figured out how to make the switch over to my world. Until today, I managed to do that with your stacked transformer, the one that Bob French gave me, which is slightly different than yours, Dave, in which there's no buck module or no boost module, and I don't even know what those are anyway, let alone how to simulate something I don't even know what it is. I just know the word. So I just know simple things, non non-electrolytic capacitors, non-polarized capacitors, just simple plain old capacitors, plain old diodes, plain old coils, air core coils. Unfortunately, I can't deal with transformers under simulation. They're a nightmare, and I don't even go there. So all my coils are air core, and yet I will arrange them to look like a center tap transformer, except there's no iron there in that model that I'm using. That's something for you to think about. So all of my coils are that way. They're air core. Let's see what else. Diodes I covered. Yeah, everything I use is just plain old stuff. Now, I did use the model numbers that Bob French gave me for the transistor and for the diodes, but I couldn't find the model number of the transformer in microcap 12, so I just used lumped air core inductors, 4 of them, 2 on each side of the mutual inductance field, the magnetic coupling, 2 on each side of the magnetic coupling, and I chose 70%. Anyway, I don't want to talk too much about what I did. I'll just show it to you. It's a long video, 3.5 hours long. I think I have about 45 minutes left to edit. And I'm going to put it up on YouTube, but I'm going to not list it. It'll be unlisted unless you don't mind me making it public. I don't mind, but I'll do it as unlisted unless you tell me it's okay to make it public. There's a lot of editing because I cough a lot. I snort. I don't like those sounds, but I'm old and my voice just isn't what it used to be. What else? And then I have to go into microcap and turn off the sound. It's very annoying. The sound comes up every time I run the simulation and something else as well, and it's very loud. So I have to mute all of those and catch them, and some of the times I'm talking in the middle of that and you miss what I'm saying, but I can't stand that loud sound. The screencast recording boosts that sound, unfortunately, over my voice to ridiculous amplitude. Anywho, so I've been having a lot of fun with that, but I was happy with it because it did everything I expected it to do. It was just a hunch, that came to me. Why don't I try a little idea that I had, and it worked because I was able to get off the voltage waveform that I was using. The only one that was successful was the impulse waveform, to take advantage of the neon bulb inside that regulator along with the diode that goes with it. It's a double combination and a certain arrangement between the two, not just any old arrangement, because I've tried all the other arrangements, they don't work. So it's a specific arrangement of one diode and one neon bulb inside that block diagram of a regulator, and everything else gets removed. So there's no need for a boost module or a buck module, unless you're trying to attenuate the explosion. If you think you can do that, ease up the explosion, but certainly it does not need anything else to contribute to the explosion of power. Now, stacking more transformers may help attenuate it. I think, basically it's a voltage multiplier, and I think this is a better version than the way most people do voltage multipliers with capacitors in conjunction with diodes, because that's more extreme. And I think the use of these transformers helps to attenuate the buildup of voltage. But that's all it is. It's a voltage multiplier. Now, once I made this conversion over to a non-voltage source version that I feel more comfortable with, and then I know it's over unity because I'm not paying at all for any of the input of energy, so I don't have to worry about recharging, sending energy back to the source. Forget that. I don't care. I don't have a source to recharge. What was I saying? Oh shit, I forgot what I was going to say. Oh, yeah, so then it starts to look like it's something slightly more than just merely a voltage multiplier alone, because some of the diodes at times start to generate power intermittently. And what else? It pulls power from the source that you will see, what the video, where it's taking it from, at no cost to us. And the load, if the inductive load, I have a 10 Henry inductive load, sometimes that intermittently generates power without a prime mover, you know? No prime movers here, and no moving parts. So the inductive load, you don't have to move it through a magnetic field, you don't have to supply it with voltage to induce current. It simply does it through reversal of current, which is the same thing as reversal of time. Yeah, the only difference between reversal of current and reversal of time is that time is the long view, we call duration, and reversal of current is the short view, or the duty cycle view, of limited to just one oscillation, one cycle of oscillation, treating it like a duty cycle of sorts by looking at well, what's the phase angle between the current and the voltage. That's kind of like looking at the on-off percentage of a duty cycle. In my book, you know, metaphorically or archetypically, topologically, it's the same concept. As far as I'm concerned, it's the way I look at it. So I can see now that reversal of current and reversal of time are one and the same thing, just a different scope, a different range of time, for specific reasons. You want the overall view, or do you want the up close to your nose view, the analytical view? You know, the latter being a reversal of current, and the former being just the duration overall. Anyway, I've said enough to set things up, you know, prepare you for what you're going to see. Probably I'll finish it tomorrow. I'm disgusted with working with it. I probably won't work on it anymore tonight. And then it's going to take forever to compile it. Yeah, a 3.5 hour video could take more than a day. It's, oh boy, just a 1 hour video can take overnight to compile. Anyway, I prefer to do things this way. And I recorded all of my work, so it's boring. But once in a while, though, if you have the patience to sit through the whole thing, once in a while I do make some aha moments in which I share something that I've learned in the course of working through the problem. Unfortunately, most of the video is not aha, and it's boring as heck. But be that as it may, for what it's worth, there's my heads up.